Professor Anand did his PhD with Professor Robert Boyd, the famous author of the nonlinear photonics, nonlinear optics book. So he finished PhD in the year 2009, and then he joined Intel. So he has industry experience for a couple of years in Portland. PhD was in Rochester University, and then he moved to Portland to Intel. And in 2013, he joined IIT Kanpur as a faculty member. And today, he is going to speak about his work on optical qubits. Professor Anand
to give this talk here. And I think this is informal enough, right? This talk series. So I'm fine if anybody has any question in between. So I can stop anywhere, unless the format doesn't allow. But
no, it's okay.
So I'm perfectly fine if anybody has any questions in between. Okay, so this is about actually coherence and partial coherence in general. Coherence is a concept that stays the same in classical world as well as in quantum world. This has been around for a while. It will remain as long as quantum is there, coherence will be there. So what I'm talking about is some of the works that we have been doing at IIT Kanpur for the last few years, especially in the context of using partial coherence for applications in quantum state measurement or quantum state detection, imaging, classical imaging, quantum imaging, and communication. So this is the FriQuant seminar, so you can add quantum to everything which is here. So that is the subject area that this talk really will be able to cover. So here is a brief outline. We'll have a very quick intro to coherence for those who are maybe not directly from this field. Although you will keep doing atom, you will definitely have coherence and so on. So just quick intro to coherence, and also then how you utilize, or how we have utilized, because this is just a few areas that we have touched. These ideas of coherence for quantum state reconstruction, also utilizing coherence for enhanced imaging and communication, especially through turbulent medium. This works right now in the classical domain. The plan is to go to the quantum domain and take it towards quantum imaging and metrology. And then also some, in addition to doing state reconstruction, one photon, we also done state reconstruction with the 2 photon. And one of the things there is that you need to be able to measure what's called entanglement, 2 photon entanglement. So we have found a new way of measuring entanglement using just single photon detection. So when you say entanglement, you have at least 2 photons involved. But apparently for some classes of states, you should be able to measure entanglement by just doing single photon detection. And then there's some bonus of kind of studying partial coherence. And more recently we have come up with something called, for a situation in which entanglement, which is usually very, very fragile quantity, especially in the photonic entanglement, we have found a way that in which entanglement actually revives itself, and this revival happens even in the presence of turbulence. So these are the things that I will actually touch. But before we begin, I just want to put, this is Professor Emil Wolf. This is 100 years. He died just a few years ago. And many of you might know him through these 2 books, The Principle of Optics and Optical Coherence and Quantum Optics. So as Professor Mahesh was saying, I was working with Robert Boyd, but in my third year of PhD, Wolf was giving a course he was like 87 at that point. And I took his course, and after that decided that from nonlinear to more of kind of coherence. So I thought I'd just put it here. Okay, so with that, we just start with a very quick intro to coherence. So coherence is the degree of order in a random field. What we mean by that, so any source or field is usually produced by a bunch of sources. You can see these could be atomic sources, and these are independent emitters. So of course, if you look at the correlation right at the source, of course, this emitter is not at all correlated with this emitter and so on. But once the light of the field gets emitted from this bunch of emitter sources, after a while they can develop some correlation, field can have some correlation. And the way you ask the question is that, okay, what is the correlation between field vibrations at rho 1 and rho 2? And how do you answer that question? Well, I think most of you know since class 11, maybe not in exactly this form, but Young's double slit, most of you know. So this is exactly Young's double slit. So, and Young's double slit actually is used for that, answering that question. So for answering that question, what do? You block light from everywhere except for these 2 points. And then you mix light from these 2 points at some screen distance away. You look at the intensity at this point, and by looking at the intensity, then you can say how these 2 points are, or how the field vibrations at these 2 points are correlated. If it's a quantum field, then it will be the wave function at this point and wave function at this point. If it's classical field, it's field amplitude here, or field amplitude there, complex field amplitude. Okay, so this is how you do it. So if you want to calculate the field here at rho, the field here will have 2 components, one coming from there, one coming from there. So that's the field at rho 1, and then the minus I omega t is the time it takes for the field to go from there to there, and that's time t1. Similarly, you will have field from rho 2, and then time it takes is t2. So that's the quantity. So that's the field at rho, which has components from rho 1 and rho 2. From this, you calculate the intensity, which is simply U star U, ensemble average. And if you just do the math, you will get these 4 terms. The first term essentially is the intensity at rho 1 plus some factor here. The second one is just the intensity at rho 2, U star U, and these are the cross terms. So if you block this hole, you will just have this term. If you block this one, if you have just this term. If you keep both open, then in addition you will have this cross term. You can also write this thing as the intensity or spectral density as S of rho. This is S at rho 1. And this quantity, which is U star rho 1, that's the cross correlation. And that has all the coherence information in it. So this thing is called spectral density or intensity, and that's the cross spectral density. So what is happening here is all you can ever measure is this intensity at rho. But by measuring the intensity, this actually has this information, and this is the information we are interested in, which contains how the field vibrations at rho 1 and 2 are connected. So in this kind of interferometer setup, what you measure is the intensity, and through this intensity measurement, you try to figure out what is the correlation information of the field. So that's coherence in general. And then you
subtract the other 2.
Yeah, so of course, so yeah, it is not that this is equal to this, so you have to find a way of kind of getting rid of these 2 terms and then just getting that. But the point is that you have this information, and now how you extract. That itself is a huge field. It's not very so easy to just can get rid of. You can get it up in some situations, not always. I'll talk a little bit about that as well. But yeah, just the fact that it is there, maybe you should be able to actually get it back, but it is not always possible, but most of the time it is actually possible.
This part is same whether it is classical light or quantum.
This part is exactly same with this. So coherence aspect is exactly same whether it is classical or quantum, as long as we are talking about classical field or 1 particle quantum field. But when we go to 2 particle quantum field and all, then 2 particle coherence is very different. So we don't have any analog in classical optics. But 1 particle quantum mechanics or quantum coherence is exactly same as the classical optics.
So only the wave nature description in quantum mechanics is equivalent to the classical thing, right? Because there is no particle.
When you talk coherence, it's always the wave, because particle will have no coherence. Yes. So whenever there's, even when you have in quantum you have particle, and then if we start talking about coherence, it's always the wave function not being localized. Yes. Yeah. And then we start talking coherence. So in that sense, these 2 are exactly the same. The mathematical structure, of course, we use different, but the structure is exactly the same. Notices are different, but the structure is exactly the same. But when I'm saying same, it is only for 1 particle versus classical. But the moment you go to 2 particles, there are so many things which has no analog in the classical optics.
So for 2 particles, I think the first equation breaks down, right? Because there is a correlation part. Is that the reason, or what is the reason?
Well, 2 particle I will not be able to cover in this one, but yeah. First of all, 2 particle you can have 16 terms because there will be 4 possibilities. So 4 times 4, 16. But you can also, in 4 particle you will have something that works completely analogous. But then you will have additional stuff that you will not be able to expense with this picture. Right. Okay, so that's that. So how do you, just answer, going back to the same question as to how do you extract this correlation information? One way, again, this is just a very limited one way, is that you look at the intensity as a function of this distance x here. And if you see this kind of fringe pattern with very high contrast, you say this, these 2 points are highly coherent, or the field vibrations at these 2 points are highly coherent. If you see the intensity, if you see the vibrations are there, the fringe is there, but yeah, it's not very high contrast, it's a partially coherent, and in this case we will call it almost incoherent. So that's how, this is just by looking at the intensity, but this doesn't mean that highly, partially, nearly, this is not very kind of quantifying it. If you want to quantify, get exactly the thing, you have to do a little bit more.
So that's the visibility of the fringe.
That's the visibility of the fringe pattern, correct. Yeah.
Finish. Because
So-
one point that keep asking since that 11th standard experiment is that even with a non-coherent source you see fringes, but the point is, where does this coherence come in from? Because if you keep going, taking this two slits closer and closer, of course you will see, but if you keep taking them far away, then you will lose the thing.
Correct, correct.
So the degree of spatial coherence goes away.
Correct.
So this degree of spatial coherence, how is it coming out from a set of random emitters?
Okay, excellent. So it's like if you go to the sun and do a double slit experiment, you will see no fringe. But the same sunlight, when it comes to Earth, the coherence part of the transverse coherence is about 100 micron. So within 100 micron, you can see high contrast fringe even with the sunlight. So you have these independent emitters, but there's no correlation. The question is, by the time the field comes here, how do you develop correlation? So first of all, there are different ways of kind of explaining it, but one way is this emitter is emitting in all directions. So, but let's say if I'm just tapping light out of there, so then that is only tapping a certain, small range of k vectors, and that small range of k vectors will have k from this source, that source, that source, that source, every source. Again, this small thing that I'm tapping here will have the k vectors from that. And so it is not that this source is getting only from one of these and this source is getting only from one of these. This has component from all, and that kind of gives you the little coherence.
Okay. Does that have to include the quantum nature of emission, the spontaneous emission process, which is random in all directions?
So you don't have to explicitly include it, but it will make no difference. So if these emitters are like spontaneous emitting, and it fits within that description, there is no issue. There is no difference classical quantum at that level.
So this is basically selection of the k vector.
This is selection of k vector. But if you are studying, let's say, temporal coherence, so temporal coherence, you have a set of frequency, and the temporal coherence right at the face of the laser or 2 kilometers away from it remains the same. It doesn't change. Of course, as long as you keep the trace constant. So for temporal coherence, you have a set of frequencies, and that range of frequency here after 2 kilometers exactly the same. If you maintain that, it remains the same. But spatial coherence is little strange in the sense that when you talk space, it is 3-dimensional. But when we study coherence, we make it 2 plus 1. XY is the space, and Z is just the propagation direction, or T. So just because of breaking it, you get additional, for example, in this case, coherence area will increase upon propagation. This never happens in temporal coherence. And that is because the thing actually happens in 3 dimension, but you are looking at its projection in 2 dimension. That's another way of kind of explaining it.
So temporal coherence is like stability of the sources, isn't it?
It could be, so there can be two kinds. So you can have a bunch of frequencies which are completely uncorrelated. So I can have a few sources with certain frequencies and in all of them emitting, and no correlation between them. For example, in CW lasers, you have a bunch of independent frequencies and it still has coherence. But you can have a bunch of frequencies completely correlated and still give you coherence. In fact, in that case, the coherence is perfect. So if it is, anything is limited, for example, if you don't have all the frequencies, just a bunch of frequencies, that will always lead to temporal coherence. Whether they are completely correlated or completely uncorrelated, it doesn't matter. But yeah, what Umakant is pointing out is this spatial coherence is a little strange, and if I go slight basic, it is because the space is 3-dimensional. but the way we treat field is like beam light. In the beam light description, you have the transverse, which is xy, and the propagation, which is z, and that kind of causes the this. And there's some theorem called the one-sided-Zernike theorem that actually shows how it kind of propagates, but there's no one-sided-Zernike for temporal coherence also.
So, for example, medium in between, sorry,
holding
here.
No, fine.
So, medium in between is, say, fluctuating reflectively, etc. Then
Uh-huh.
you see coherence also.
So that will add its own spices,
Okay.
and whether that is causing. So temporal and spatial, these are not completely separate things.
Yeah,
Because
at a given space, you see how the phase changes with time, right?
correct.
So that can happen due to.
So I can look at it from example like this same T1, same T. So equal time. When we say special coherence, usually refer to equal time coherence. But in Maxwell's equation, you have both R and T.
Yeah.
So you can't really
But
separate.
temporal means you fix the space and change the
Yes,
phase versus time.
Yes, but you can't do always. I mean, in extreme cases, you can't really separate space and time. But typically, you do spatial coherence and then separately, and you can always kind of combine it.
Okay.
So, okay. As I already said it, the classical wave mechanics and quantum mechanics, there's as long as this is one particle, it's almost the same. The mathematical structure, I will just kind of put it. So if you have no randomness, in classical wave mechanics we represent it by field. In quantum mechanics we call it, I'm just drawing kind of a parallel here. In quantum mechanics we call it, in quantum mechanics when we say no randomness, this is the external randomness I'm talking about. Quantum always has that intrinsic randomness there, and that you cannot get rid of. So for when there is no external randomness, you write a field as you can write a field as a coherent superposition. So this is a field in the time domain that you can write as this Fourier transform as you know, the superposition of a bunch of frequency components and so on. Similarly, in quantum mechanics, you can write the state as a superposition of frequency, space, states, and so on. You can have a field in position, space. This you can write as a superposition of modes over the spatial frequencies. In quantum, we do the same thing, just the notations are different. This is time, space. So to complete it, this is angle. So you have signal or field in angle, and this you can write in terms of this discrete Fourier transform, where L refers to, in the quantum at least, it's called the orbital angular momentum index, but in classical it's also called the azimuthal index and so on. In quantum, you can just write this same thing. I'm just drawing parallel. This the state notation will go like this. I guess people are not familiar with this last part, the orbital angular momentum. So I just go really quickly as to what it means. Orbital angular momentum. So orbital angular momentum of light is actually not a new concept. It's been there for a while. So if you have a paraxial wave equation in cylindrical coordinates, that's how it looks. And a solution to that is this so-called Laguerre-Gaussian mode. We don't need to go through it. I just want to kind of show the solution. So only thing I want to concentrate upon is that this has a phase. The phase dependence of this mode comes only through its e to the I L5, and this has two indices. This solution L and P. And of course these are the. So if you look at the transverse intensity of these modes, that's how it looks. And these modes are of course characterized by these two indices P and L. So P equal to 0, L equal to 0, that's a Gaussian beam, and this laser pointer is very, very good approximation to this Gaussian beam. So that's actually, this is actually laser pointer actually solution to the paraxial wave equation with P equal to 0, L equal to 0. But you can also have P equal to 0, or let's say P equal to 0, L equal to 1, that's called a donut beam, or what do we call it? Vada? No. What Vada has a hole in the center, right? So that Vada beam. And this is bigger Vada, beam with L equal to 2. You can also have Vada with double ring and so on, that's P equal to 1, P equal to 2. So this is how, and these are the modes that if you can actually make this, that's how it will actually propagate as double ring or triple ring. It won't change its state. And if you look at the propagation of this beam, so for example, L equal to 0, at any given Z, this is how it looks like. For L equal to 1, the phase changes by 0 to pi. For L equal to 2, phase changes by 0 to 4 pi once you go across. And if you look at it as a function of Z, of course that's how it propagates the phase front, but in this case it makes a single helix. In the other case, it makes a double helix. These were all known. These are all known from the classical.
So this is over one wavelength.
Over one wavelength, correct. Over one wavelength. But what got people excited about orbital angular momentum is this result in 1992, which actually showed that orbital angular momentum per photon in an LG mode is h bar L. Again, no extra quantization here. Those were worrying about second quantization. Now, the quantization is still the same, just the energy quantization. But in this mode, if you collect enough field from this, such that the total energy is h bar omega, then corresponding to that energy, the total orbital angular momentum will be h bar L, and where L is an integer. So now, since you have an integer here, of course, quantum information, you are excited. Now you have a basis which is discrete, and that is what you need in quantum information. And this basis is above and beyond the polarization basis that you get, which is only two-dimensional. But now you have literally an infinite dimensional basis at your disposal. So a lot of use, the applications of, I think I need to update this. This is coming from 2012. People have shown terabit data transmission using OM multiplexing. Again, this again is the classical, but now people are kind of started to use more of orbital angular momentum mode for classical and quantum information. Okay, so that's quick detour for the intro to orbital angular momentum, and we will hear back. And so here, maybe you don't identify these completely, but if I take a projection of the state on the phi basis, then we write it as kind of the wave function in phi, and that has this structure. And now you can see the classical amplitude of the wave function. They're pretty much the same mathematical structure. So that's when there's no external randomness, but then when there is randomness, so in classical you cannot talk about field, you then talk about correlation function. What is a correlation function? At least for the angular domain, W phi 1 phi 2 will be star phi, phi 1 be phi 2, and there's an ensemble average. Ensemble average means you take a state, you take a multiple copies, and you take an average. And that is the ensemble, the idea of ensemble. This is a very central concept to coherence. And if I use this expansion, then this correlation function kind of looks like this. Of course, there's nothing random about it. The randomness only is in the amplitude, so it will look like this. Now, in the quantum case, when you have a random process, we call it mixed state. In pure case, in the no random case, a pure state. So, taking the same example, then we don't instead of correlation function, we have this density matrix, which we write as in this case like this. There's a ket and bra, and then we do the ensemble average. And if I use the same notation, I can take the projection in phi and phi 2, and then it looks exactly the same as this thing. And so this is the density matrix element. So the density matrix element in quantum and the correlation function in classical, again, they are exactly the same thing. So if I take even a particular example, when this alpha L1, alpha L2, they are completely uncorrelated. That means we are dealing with a bunch of OM modes that are completely uncorrelated. In that case, this ensemble average will be just a delta function. And if it is a delta function, then this correlation depends on phi 1 and phi 2 only through the difference delta phi. So this then becomes this is probably tiny delta phi is delta. And in the quantum case, when it's not correlated, this rho becomes just like a diagonal mixed state. The density matrix becomes diagonal. So this is called angular correlation function. This is called the OM spectrum, and then this is called angular Wiener-Khinchin. This is just for adding information. This is okay. So that's a quick intro to coherence. Now, how the study of coherence, we have been able to kind of do a quantum state reconstruction. So I'll show you a few works that we have. So the state measurement is very important in any quantum information, because you have to have detector. Unless you have a good detector, you can't do much about it. And now that people have so many applications in mind using OAM, you do need kind of detectors. And believe it or not, you don't have good detectors yet for OAM. So a lot of work, maybe I should not go into the details of all of those, but there's a lot of background work in this one.
And there are no commercial detectors for OAM?
Yeah, okay. So as far as commercial detector, this was like 2001. This is the best, well, this is the best commercial detector.
I didn't understand. What do you mean by detector? You see the modes, right? No. Or do you mean creation of coherent? No.
No, creation is easy.
Creation is easy.
Creation apparently is very easy, but say detection meaning like, well, when you know there's a mode that you have created, you don't need to measure. But it's like light coming from bulb. Now, what OM it contains?
What all the OMs?
What all the OMs?
Superposition of different.
Superposition, non-superposition. What exactly the state is in the OM?
If it is pure, you can see, right?
Well, if you have produced yourself, then you know it is what it is.
No. If somebody produced, but you still can't tell the helicity, right? Or something.
So just saying that the helicity, that is one aspect, but even if you have a pure state, but exactly what is the pure superposition? If it's 2-dimensional, very easy. 20-dimensional, very difficult. 200, impossible. So, and if it's mixed state, then you know. So yeah, it is still evolving. Not easy. But the more the you have the, I mean, the kind of experiment that people are able to do now is because they're better and better photon number detector, just the detector. So OAM, I think it will still take a while to kind of get there. So without kind of going, maybe I can go through one. So the one most popular one, and the probably whoever is using kind of mostly does it this way, is that you have a field coming, unknown field. The field could be from tube light or sun or anything. Now you want to know the OM content of this field. So what do? You put something called like a diffraction hologram, and in this electronic version it's called SLM, spatial light modulator. And this then you use in connection with single mode fiber. Now single mode fiber, it can only couple a Gaussian mode, which has L equal to 0. So if a single mode fiber collects everything, then you know this is L equal to 0 component. So what do? You put a diffraction hologram, and you put this diffraction pattern, which actually diffracts. Let's say you put a diffraction pattern minus L. Now this minus L diffraction pattern actually diffract plus L component of this field and put it in a single mode fiber. Turn it to L equal to 0, and then can get a single mode fiber. So by changing this hologram from minus for different L, you can actually get the content of that particular L in the input field. So this is the most common way of actually doing it. But fiber has very non-uniform efficiency for different incoming L. That is a problem. And beyond plus minus 10, L equal plus minus 10, it will cover nothing. And so then there are other ways of doing it, but you know, there's several, mostly dimensionality requirement. It doesn't go beyond certain, the dimension 5, 10, but in OAM people are thinking very high dimensions. So of course you have to have a detector that works very high.
But if you have mixture of L state, can you still use that method?
Yes. So the idea is you put a hologram, and this is kept at the first diffraction order.
Okay.
So the point is, if I put a hologram with minus L phase pattern without actually going to the decay, then only plus L coming from the field will get diffracted into that order. Will turn it to L equal to 0, and hence can get coupled
So
by
why don't, I mean, okay, they have to be coherent, I think. You take an L equal to 0 beam, Gaussian beam, and then with the incoming beam, you just take the diffraction pattern, I mean interference pattern, by putting this phase imprinting on this known beam, which is the L equal to 0 beam. You change different modes which are going to interfere with the incoming beam, and then look at the projection basically.
Right, but that method will work if your L equal to 0 and the beam that you're measuring is from the same source.
They have to be phase coherent.
Phase coherent. That means they have to come from the same source. That means you must have manufactured the field yourself. But if it's coming from sunlight, there's no reference, so you can't interfere. So in that case, it becomes actually very difficult. But if I'm then looking at the emission from some, atomic setup or something, I want to know its OM. I have just no reference.
I have to.
Yes, yeah. So we came up with this one way of doing OM measurement. This is for the kind of again, this is not for all the state, only subclass of state, and so diagonal mixed state. And
about,
yeah.
from the last slide, so if your L is different, then every time do you have to change the hologram?
Yes. So this is one by one. Yes. But since hologram you can do it electronically, so you can program it and go for T, and by the time you come, you have all the scan done. But earlier actually people were doing this with the physical element, with the glass piece, and there it's almost impossible. But yeah, since these holograms are electronic, you can just display it, through LabVIEW, and keep doing through the program. You don't really do it. So within a minute you can actually scan 20 modes. It's very easy.
If you can do that, then it's not that difficult to escape. I mean.
Oh, so what is the point? Then it is done, right? It's a done deal. So it is actually a done deal. But except that if you care only about, let's say, 5 modes, then that method works for you. But if you have, let's say, 50 more, 100 modes, it doesn't work. Not because SLM doesn't work, because fiber has a limitation. So you are coupling it through the fiber, single mode fiber, and single mode fiber couples L equal to 0. Now when you are turning an L equal to 10 mode to L equal to 0, versus an L equal to 20 mode to an L equal to 0, versus an L equal to 50 mode to L equal to 0, the sizes are different. And then the coupling is different.
How about just using a spatial filter, microscope objective and the pinhole?
Whatever you do,
it will be the same problem.
Yes, because that will have a definite size. Then you have to have a size.
So the mode matching changes.
Yes. So then, since
so
you claim that it's an independent unknown field, then that is difficult. Did I answer your question? Okay, so we actually. I don't think I have much time, right? 20 minutes?
Yeah.
Okay.
25.
25, okay, I'll go quickly. So we made this detector. This is very simple. This is a Mach-Zehnder interferometer. And the only thing you see is that odd and even number of minutes. Other than that, there's no difference. But this actually makes a huge difference. So a reflection actually flips the wavefront along the reflection axis. So let's say I have OM mode which has e to the minus I alpha, and I put this mirror as a reflection axis. This actually will flip and the wavefront will become like that. So the e to the minus alpha actually becomes e to the I alpha. So in this case, if this is my field, part of it goes through, the field goes through this or that, and then this is my kind of superposed field. And so you have e to the I alpha with an even number of reflection. You will have e to the minus I alpha with even number of reflection because it remains the same. Equal to the plus I alpha with odd number of reflection. And if you just carry out the intensity, in this case you will actually get like this. So this is actually same as what I was showing for this one, except in this case you see this is S rho and this is W rho 1 rho 2. But in this case, because I have this inversion, this intensity depends on phi and this correlation also depends on 2 phi. So functionally they are almost the same, which is not there in this case. And so by measuring this, you can actually get this out. But then again, as Mahesh was saying, this doesn't seem straightforward because you have to get rid of this. But again, right now it is in principle that you can do it. So maybe I can. So what you can then do, right? So now I'll show you a trick by which you can actually get this directly. And what is that trick? So this is my field from the last slide. This field I'll make it even more complicated. I will add some noise, and of course noise doesn't depend on interference. It is just there. So and this delta is a phase difference between these two arms. So what do? You take the intensity measurement at two different values of delta. Let's say delta C, delta D, and you take the difference intensity. And if you do that, you see this difference intensity has this delta I, which is the difference in this noise term, and of course this term. So as long as the short-to-short noise is the same, that means the background is same in the two measurements, which is of course usually the case, then this becomes 0. And your difference intensity becomes directly proportional to the correlation function. And functionally, these two are the same. So at least in this case, for diagonal mixed state, what we can see just by doing this difference intensity, I can directly get this correlation function over there. Okay, and once you have the correlation function, then you can Fourier invert it and you can get the OM spectra. So by measuring doing two intensity measurement, I can get this OM spectrum.
So you are saying delta depends on the noise?
delta noise doesn't depend on delta. If noise doesn't depend on delta, then I think you can actually do this. You can put this as 0. But if it does, then of course you cannot. But we are just putting it as a kind of symbol here. But the idea is that it doesn't depend on noise. Sorry. If it did, then you could not, get rid of that term. And so once this goes away, then I don't need to know, because here to reconstruct this, I need to know K1, K2. But now I don't need to know K1, K2 because this is directly proportional. So of course you renormalize things anyway for the energy conservation, and then this is directly.
But second term also should go away, right? When you take
This term, no. Yeah, it does go away. So there's
even third term, I mean last term.
No, so last term has cosine, let's say delta C and delta D. So
Yeah.
this is so this cosine delta C minus delta D.
So that depends on mass. That's why it's different delta.
No, that's not noise. Delta is your parameter in hand.
Delta is the parameter, that is the phase
Okay,
difference of
okay.
the two arms.
Okay.
Is the phase difference of the two
Change.
arms. Yes.
But-
Yes. So you change delta. It doesn't need to be 0 and pi, but if it is, signal to noise is better. It could be any delta C, delta D, but of course we try 0 and pi. And then at that point it becomes proportional, and then you don't need to worry about this K1, K2. It just, you can get there.
I have a.
Yeah.
So does this depend? I mean, do you beforehand need to know the dependency of the noise function on phi?
No, you don't need to know anything. Only thing is that, let's say within the few seconds that I have made these two measurements, delta C, delta D, the noise floor should not change. Whatever is the noise floor, I don't need to know. It's just that it should not change. As long as that assumption is intact, you can do
But
this.
how do you make that assumption before? I mean, there must be
Well,
some constraints to.
Well, in physics, experimentally, you make some assumption, you try experimentally, as long as it works, then you announce, yeah, assumption was correct. So, I mean, if it is completely off then I'll show you some results, then you can decide whether it actually worked or not.
So this is a spatial noise.
This is the spatial noise, yes.
Um,
Oh, this is not the photon number noise, correct.
Right.
This is not the photon number noise, correct.
And I think Mahesh probably the confusion was the delta subscript on IN.
Ah, okay, sorry.
No, I
This is
thought-
not photon number noise,
I
correct,
thought
correct.
noise is playing an important role. It is just you are explicitly saying because there are two different.
Yes, and in experiment, yes, you do have the noise. I mean, I'll show you some experiments.
It is
The
not
noise.
playing an important role. It is not playing. An
We are
important
able to kind of bypass that, the entire noise effect, correct. But these are spatial, not photon number.
So if you take
Okay.
out noise, sorry,
Before-
if you take out noise also, you won't get the same result. You can do the measurement at
No,
two
no,
different
here
distance.
you cannot take out noise. You have this K1, K2. So you need to know the splitting ratios and all exactly before you can actually subtract W from I. So here we just made this little more complicated. That let's have K1, K2, let's add some noise as well, which is of course there.
But why do you add noise?
Yeah, I think they are just trying to do the minus so that the K1, K2 terms cancel out.
Correct.
So basically measuring it at different
But you
deltas
are
because that's the
anyway
only
changing
variable.
delta, right?
But
Yes,
you can.
That's enough, right?
So why?
No. So for example, this is your source, right? But in lab we can have somebody's cell phone display being on,
But that why do you add deliberately?
because there will be something always. So in this modeling, you this kind of modeling, you assume there is no other source in the lab.
Yeah.
It is completely just an unknown source coming in. That you have the blinking LED in your computer or your computer screen. So that there's always the noise floor is always there, and that you will see in the experiment. So just because we could, I mean that this method was able to take care of that noise floor as well. So you don't have to kind of do a background subtraction. So in this case, I don't have to do any background
But you
subtraction.
don't have to add noise deliberately. right?
No, it's not. No, noise is always there. The
Correct.
background is always there in the optical
Correct.
signal. Here we are explicitly including in the model.
Okay,
Because-
including in the model.
Yes,
So
yes.
not in the experiment.
No, not in the experiment.
Okay.
No, experiment is
That was-
experiment. It is always there.
Yeah,
But
but
it
we are
is-
not adding noise.
No. You don't want to add noise. Yes.
So, I mean,
Yeah.
that was the confusion.
No. You don't add. No. Sorry, you were asking something?
Yeah, so I was just asking that the thing that you were trying to do that I could understand was to remove this K1 plus K2 by 2 pi term.
Correct.
And by doing subtraction that becomes easy.
Uh-huh.
So that you are doing using delta parameter.
Correct.
but you can do that using phi parameter if you know how W varies with phi or something.
No, you don't know that. That is
Oh,
what you want.
W you try
W
to
is
find.
W did 2 phi is what
Okay.
you need
so
to find.
K1, K2, if you do that won't happen.
So
Okay.
either if you know K1, K2 exactly, then of course if you know the noise exactly, then you can always do that. But knowing K1, K2 is an impossible. Knowing noise or background noise is also impossible.
So only delta is the parameter that you are varying in the
Correct.
setup.
Correct. And then we measure intensity as a function of phi. Right? Okay. So right. So then we did this experiment. We made a kind of a lab synthesized this OM field, and here we were trying to make a Gaussian spectrum. So if you just take a delta equal to delta C, this is how the pattern on the CCD camera looks like. If you look at its I phi, I is a function. This is a 2-dimensional, but then you plot it as a function of phi. This is how. So you see the kind of noise. This definitely is not what we wanted. And if you then do the reconstruction by kind of guessing the value of K1, K2, this is the kind of reconstruction you get. You take another shot at delta D. This is the kind of spectrum you get. It is noisy. That's the reconstruction. You take the difference. That's the difference you have. Of course, this is less noisier than the other one, and then now the construction is much better. So this was Gaussian. We also tried rectangle. Same story here. Maybe not as impressive, but again, this kind of cleans it up. And so we wanted to kind of do it for single photon down conversion as well. So this is going to the entangled state. Since I don't have much time, so I'll skip the details part. I'll just show you the experimental result that we have. So in down conversion, what happens? I'm just looking at the OM spectrum of one of the photon that is actually emitted. And this is a very natural process. This is a nonlinear optical process. One photon gets absorbed, 2 emitted. One goes this way, one goes that. This is called signal, this is called IHub. But it comes out with a lot of OM content. And this is the 2-photon state. So whenever signal is LH bar, idlet is always minus LH bar and so on. But this L can take any value. And usually this is very broad. So we wanted to make how broad this is. And through the math, you can actually show this spectrum is same as the OM spectrum of the individual photon. So in this case, when we did the experiment, this is the one-shot result you see. This is again noise, so the reconstruction has some issue. This reconstruction has some issue. If you put it together, this cleans up, and this is the kind of reconstruction you get. So I mean, you can see the 2-shot, and since this is naturally produced, we were actually producing with the Heaney in the lab, so maybe there was a generation error. So this was at that 82-dimensional state we were actually able to get. And then, of course, this was a little troubling as to why this is not fitting. So then we did slightly better modeling. And with that, we could actually show by tilting the crystal and taking as a parameter, we can go even better fit. And we were able to kind of generate and measure the same states up to 229 dimensional states with just 2 intensity measurements. But this is only for the diagonal mixed state kind of thing. So next we actually went to for measuring pure state. So I'll skip this. How much time I have? 10 minutes? 10. Sure. So let me skip this. So again, the other one was when the diagonal state is, when the density matrix is diagonal, we were able to kind of get a state, and we could do up to 250 dimensional state. We then worked out a way of measuring the pure state in the OM basis. This was using 9 shot, not just 2. And so in this case, we could go up to 11 dimensional state with 90% fidelity, but higher dimensional we could not actually go. So that shows how difficult this one is. And then again, the efforts are on for doing it for the more general state. Okay, now going to the next one, partially coherent light, and its use in imaging and communication. So we have some way of kind of generating this partially coherent light, some way of kind of, so we are able to produce these kind of partially coherent light in the lab. And this is not the regular Young's interference you see, this is actually W. So we can generate W that has this kind of structure. Yeah, this is also and then we have also developed a way of kind of measuring. So Young's double slit is pretty old. We have some way of measuring the complicated coherence function. So this is one example. We can have coherence function like that, and that can also be measured. That's one is theory, one is experiment. Here is one use of using especially partially coherent light for imaging. The idea is simple. You have a source, you have an object, and you want to image it through scatter. So I just want to show kind of two results. So if you use a helium neon laser, which is spatially completely coherent, then you see this is the for a given object. Let's say this is its ability to kind of image. In the same setup, if I use this partially, we call it propagation invariant coherent source. With that, you can see the quality of this for a given scattering. If you increase the scattering strength, that is the helium neon laser or a coherent source does no imaging, but a partially coherent source is much better. So, and in fact, this you see in the when you use your cell phone for imaging through lens. This one is not using any laser; it's using an LED, which is a kind of incoherent source. And this is all incoherent source. So, incoherent source in the presence of scattering or turbulent medium is a better way of doing imaging than using spatially completely coherent source. So that is the kind of whole idea without going too much into detail. And we have ways of kind of controlling the structure of coherence, and that gives me added advantage for imaging.
This is counterintuitive. Can you?
Okay, so this is okay. Okay, so if the world is ideal, there is no difference. You can do imaging with perfectly coherent versus partially coherent. But of course, the world is not ideal. So, I mean, even this distance. So, if I'm using a completely coherent source to kind of illuminate some face or something, it will have some edge. And because the coherence is perfect, you have a lot of speckle pattern. But in the partially coherent, the speckle pattern, is not as much. So that actually adds to your advantage as far as imaging is concerned. So that is if you say basic physics, that's how it works. So the ensemble averaging of that speckle pattern, it overall smears it, but the features can still be covered. So.
Is there a degree to how partial passenger?
Yeah. So spatial coherence you can quantify. There's a degree of coherence, the quantity that can go from 0 to 1. So you can.
So does it improve with as in how like the worse the
Okay, that's a very.
Is there optimal?
Yeah, is there?
Yes, there will always be an optimal degree of coherence that you want to use, and that will be decided by the kind of scattering you have. So if you have more scattering, you want less degree of coherence. Of course, the degree of coherence, scattering is more, overall quality becomes bad. For example, this is more scattering, so this quality is definitely worse than this. But with the same scattering, if I use a completely coherent source, you can't see anything. But this source, I can at least see something. So this gives you the ability to image up to some extent. In the case of yes. And of course, we made slightly more. This I will not go into detail, but you can see I have not put in the partially coherent source here. There's a new kind of source we made. This is a huge scattering constant. In this source, nothing. But this specially designed partially coherent source, you can actually still see something. This actually we got this alpha by almost grounded, microscope glass slab, and then wrapping this tissue paper on that, and then we were imaging through that, and we still could see something. So yeah, you have to do all the jugaad when you are doing experiment.
Can you reproduce the? You have to get the same brand of tissue.
Yeah, I mean you could get maybe alpha not 142.8, but maybe 130 as well. So, I mean, if you try, you see nothing through that. You will see nothing, but yeah, we will trying to measure. Okay, and then there's in communication. You see, if you have it relates to the same question. If you have no turbulence, R naught infinity means no turbulence. Then whether it's more coherence or less coherence, it doesn't matter. It's all the same. But if it is actually a turbulent medium, then you see this partially coherent field. So the field that has less coherence works better or propagates better than the field with more coherence. So this robustness of this optical field through turbulence is better if it's partially coherent. Okay, so then we go to this one quick thing. This is about entanglement. Now entanglement, those of you know, this is one type of entanglement, is position momentum entanglement. And one way of kind of explaining or defining it is an entanglement. You always have two particles. So for example, if you look at the position of this particle, then the position of the other particle, that's conditional position measurement, let's say it is delta x. And if you again look at the momentum of this particle, then the conditional measurement, conditional momentum measurement, let's say delta p. If these are position momentum entanglement, then this product can be less than 0.5 h-bar. That's a Heisenberg limit. But if these two particles are entangled, then you can actually have that. And again, we have found one way in which we can measure this position correlation, momentum correlation, and this number that we have obtained. And this is just by using EMCC, just the intensity measure, no coincidence, because if measuring two particles simultaneously, that's experimentally quite challenging. And with this, just because we have too much signal to noise pretty good here, this is the best violation of EPR entanglement that we have seen. This kind of came up this year. And then finally, this is the bonus thing of studying that partial coherence. This is also an entanglement only. So in addition to position momentum entanglement, you also have what's called angle OM entanglement. Now, what is angle OM entanglement? So if you can imagine a very, very infinitesimally thin slice here, which you can call theta I equal to 0. If you get a photon here, then you can say, okay, I have detected photon at theta equal to 0, the first photon. Then the second photon corresponding to that they are entangled will be found in this theta. See, you can do similar thing for its L content, and if this delta theta delta L is less than 0.5 h-bar, then you can forget this factor for now. Then you can say it is angle OM entanglement. So position momentum entanglement, what you see invariably that it gets produced by, you can produce it, but after a while the entanglement actually gets lost and it never comes back. And this happens within a centimeter or so. But for angle OM, what we found that yes, you also lose angle OM entanglement, but it actually revives back on its own without you doing anything. You just propagate it and it actually revives back. And so that's why we call it propagation induced revival of EPR entanglement. So this is the numerical simulation showing why it works the way it works. So that's the experiment. This is the here we are measuring the position, the delta x angle for making the momentum measurements. It's a very similar setup, but just the imaging conditions are different. And then we set up the experiment for making orbital angular momentum measurement. And if you put it all together, this is what we see for the position correlation, momentum correlation, and the correspondingly the product actually looks like that. So the position and momentum delta x delta p, it looks like this. These are the experimental values. That's the theoretically what we kind of expect. So you see the entanglement gets lost and it never comes back. And this is the limit 0.5 h-bar. And if it is below the product, then you say it is entangled. If it is above, then you say it's not entangled. In the case of angle OM, you do see that the entanglement actually gets lost, but it actually does come back. So it revives. Now the even more interesting part was that now let's say if I introduce some turbulence, and of course turbulence affects everything in the worst possible way. So if something is entangled, it goes through turbulence, of course you will lose entanglement. But we found that even after going through a turbulent medium, entanglement revival still happens. But of course, before if it was happening at z equal to 24 centimeter, now the revival is happening at z equal to 35 centimeter. So if your entangled photons have gone through some turbulent medium, what you do is just propagate a bit longer and then the entanglement kind of comes back.
That's better, sir.
Huh?
Isn't it better?
You do nothing, you just walk a little bit and your entanglement is back. So this can be very useful for the application that actually use angle OM entanglement for imaging, metrology, communication purposes.
What must be the reason for the revival?
What is the reason for the revival? Yours for the same question?
I had the other time also.
Okay. Yeah, I don't know properly. This has come out this year, so it works. But again, I have not really worked out I can give an intuitive picture, but we may not be very happy. But the main reason is it is the way the two bases, position and angle. Position basis is negative infinity to positive infinity, but angle basis is 0 to 2 pi. It comes back on itself. So because of the nature of the basis, the correlations actually roll back. It's a more mathematical thing. In fact, if you have some bunch of runners, on a circular track, and if you start randomly, and if they continue the same speed, eventually they will all come back the same. Yes. So it's similar kind of argument here, in a very broad way that actually works here. I don't know if you're happy with that explanation.
Yeah. Is there any lifetime in this thing here? Because in general, when we deal with quantum systems, they have a finite lifetime relaxation. Is there any such factor?
Photons are the boss in that sense.
Yeah, so they have very long.
No, I don't have any issue. So but they travel very fast. So if you can move with them, there is no issue. But of course, you only have the time until they are in your setup. As far as doing something is concerned, if you can delay it by doing multiple reflections and so on. But photons at least have that advantage.
So this.
You can ask.
Yes, you mean while these guys settle, yeah.
Does this curve is asymptotic, or entanglement goes back again, disappears again and then comes back?
Well, that's a very good question. It doesn't come back. So, but it can come back if the trace is not preserved. That means if I, as long as I keep collecting, because as the field is coming out, there is a diffraction, and nobody can beat diffraction. So there will be, because of diffraction, there will be divergence of the beam. But as long as you can cover the whole beam, you can collect the whole beam, this will continue this train asymptotically, almost close to zero.
And what is actually turbulence in physical terms? What you?
Oh, we use a blower heater.
Okay.
Blower heater, hot air, and that gives you kind of turbulence. So that's a physical thing we use.
But that's like an open system.
That's an open. That's a real turbulence, open system, and since this was.
And I have another question: for how long the system is exposed to that turbulence?
15 hours. One data point was 15 hours.
No, I mean when it's traveling in that path.
So the turbulence will be a few centimeters. I mean, yeah.
So
I mean, the air is blowing, the heater you keep. So maybe 10 centimeters.
So it's like you expose the system for a short time to open bar.
Yes.
And then you close it back again.
Short distance, and that distance will translate into time, correct?
Yeah. And then you close it back.
In nanosecond or sub-nanosecond, correct?
So this entanglement, does it again go back to zero? Like, does it have a oscillatory feature or?
So if zero is the best. So zero, delta x, delta p equal to zero. That means perfectly entangled.
Yeah, but at one point it loses entanglement.
Yes.
And then it goes back.
Yes.
But does it remain there or does it oscillate?
It remains.
After?
Yeah. So again, same question. It remains there as long as you keep the trace preserved. That means you don't lose the system. So if you keep collecting the whole thing, it will. So as it propagates, I have done it with z equal to 60 centimeters. But let's say you go 1 kilometer. But this size beam, which till 60 is like 1 inch or so, you can 1 inch collection aperture is enough. But 1 kilometer definitely become like a meter. But if you do have a meter aperture lens, you will see actually it's downward trend only.
So
but if you lose there, then entanglement actually you can lose entanglement.
No, but wherever you are putting turbulence and you are saying that the point has shifted, consider you again put turbulence after some centimeters. So does the same thing happen? Like
yeah, of course. So if so that's again a very good question. So you're saying this is turbulence. Of course you lose it, but if you put turbulence right there, it will again go back up.
It will go back.
Yes, yes. And then if you just leave it, then it will again start the same trend. But even within turbulence, you should not lose the field. Turbulence will cause the field to scatter. It will go this way, that way. But as long as you collect the whole field, it will still start the downward trend after the second turbulence.
Another question that is little bit.
Can we take the questions and let him finish?
Sure.
Okay, so I was almost. So this is the summary. So what I have talked is efficient quantum state reconstruction through coherence function measurement, and I think I was able to kind of convey this state reconstruction is actually a very difficult problem, and for some classes of state, we have actually been able to show that there can be efficient way of doing it. And then I'll show you some way of partial coherent light being better for imaging and communication. On this I didn't talk in much detail, but we have a way of measuring two-fold entanglement with just intensity detection, and that gives me a much better signal to noise than the methods that are based on coincidence. And then this feature of revival of two-photon entanglement in the presence of turbulence. So again, thank IIT Kanpur, the JCRB and Quest project for the funding. That's my group at IIT Kanpur, slightly over the picture. And again, if anybody here, I mean, when we go to talk without taking your permission, again, if you're interested in any student, PhD, postdoc, we are looking for people there. So yeah, so thank you for the attention.
Very counterintuitive. We pay more for coherence.
Yes, yes, yes.
So you say that going otherwise
Is yes, at least for some
so
purposes.
is there any tunable this partially coherent source?
Yes, so that
Where
is
you can tune this partiality.
yes. So okay, so
Because in IHub we think that
very quickly, I didn't talk much, but so we have been working in that direction. So this is actually a perfect example. So this is a very simple idea. You have a spatially completely incoherent source. Like an LED is a very good example of completely incoherent source. Now you put just this at the back focal plane of a lens. Okay. Now since this is a completely incoherent source, each source is independent of each other, with every other. And so each source after the lens will become like a plane wave. And now these plane waves will be completely independent of each other. And if I have that equation, oh I do. So in this case what you find is that the correlation function in this source, the correlation function is actually the Fourier transform of the intensity expression. This intensity is just of this partially coherent source, the completely incoherent source. So if you want to structure whatever structure of the correlation function you want, take the Fourier transform, and that should be the intensity pattern of the partially coherent source. So you can cut your LED in that shape. You can get any shape. So that will be one very.
I see. So this is a very controlled way of
This is very
producing
controlled, yes.
partiality.
Yes. So I'm actually looking if I can have a, let's say 512 by 512 LED bulb.
So this is not there in the market, right? So
I
you
have
can
found
pitch
maybe
into
8 by 8,
product.
16 by 16 kind of things are there.
No, but the whole product, is it available as a?
No. This is in principle. This I was able to buy on Amazon. This is a 850 rupee.
Okay.
850 rupee, not 1000. And this is 850 rupee. Any this regular LED bulb, you just strip off all this, covering and all that, and you can see this 9 LED. And with this, so with all the 9 LED, this is the kind of structure you get. With one source, you will get more like a Gaussian. With two, but if you have 5 to 5 to like this, then you just give you a wish list. That's the coherence function I want. Get the Fourier transform, and that's the structure you put, and you get the source.
So this can be pitched into a product.
It actually can. I was surprised that there is nothing like
Nothing,
that.
right?
Yes. I was actually.
I hope will be very interesting. You can send the proposal.
Oh, excellent.
Yeah.
I mean, technology-wise should be available. Just integrating those many LEDs, the technology should be available. But market, I don't think it's commercially available. Many people have
Excellent.
it,
Yes.
So this angle and space entanglement, the distance when it starts, when it revives back, does it depend on the L number and how?
So when we say angle OM entanglement, no. When we say angle OM entanglement, we are not referring to a particular L. So you have to have this multimode in L. So of course the L width will have some effect on this delta theta and delta L, but in general, I mean, you assume a larger width, but that shape, well, I haven't studied that. Maybe different L shape and how that exactly changes this distance. I think it will have some dependence, but we haven't actually seen.
Yeah, can you go back to the revival slide? This is that graph.
This one?
Yeah. So here, at what value of Z you are putting the turbulence?
Turbulence one, we're putting at about 15 centimeters.
15 centimeters. So my point is that momentarily you are making the system open, and it is losing the entanglement. Now if it is reviving, so those two degrees of freedom must somehow interact, right? So because it's again a closed system and it is getting entangled by its own. So is there any that kind of interaction?
No, the system was never open, by the way.
No, due to the short period of time.
No. Even then the system is not open.
Okay.
It has, you can definitely say it has interaction. Well, if that is the that is also
Yeah,
a definition
so
of
that's what I
open
meant.
quantum system. So yeah, so yeah, for that you can consider open quantum system.
And then you're closing it again.
And you're closing it again.
But
And because of that, you open it for short time or
you
short.
get some information, but somehow you're gathering it back.
Yes.
Uh,
Yes.
So in the propagation, is there any interaction between those two degrees of freedom? Otherwise,
Which
it's
2 degrees of freedom?
the 2 degrees of freedom which are getting entangled here.
No. Sorry. So degrees of freedom are not getting in the way you put entanglement. So degrees of freedom are not getting entangled. That's not what we put it. For entanglement, you always have to have two bases, and these need to be conjugate bases.
So here the Fourier transform basis, right?
Usually,
Okay.
the Fourier conjugate basis of theta and L are these are Fourier conjugate basis.
Right.
Now you can have, let's say, this delta theta. Even classically delta theta can be 0. And again, even classically delta L can be 0. But of course, this product delta theta times delta L, that can never go below 0.5 h bar. But if you do have this delta theta times delta L going less than 0.5 h bar, then you say entanglement.
You're
Why?
witnessing an entanglement.
Because you have tight correlation in both theta and L. And only if you have correlation, simultaneous correlation at two different bases, that's when you call entanglement. Even in polarization entanglement, you have to show entanglement in HV basis and let's say some other basis 45 minus 45. These are kind of like conjugate. So for entanglement, the only way.
I got that, but the point is when you're opening it and then it's closing, the revival is very counterintuitive. Not, and also a closed system, it is reviving. It's very interesting.
Okay, so maybe I can rephrase your question. You are a little worried about why is entanglement you're thinking was a conserved quantity, right? So entanglement kind of like conserved. So if I'm kind of preserving the trace, so why is there a decrease, increase, losing,
So
revival?
decrease we can understand because you're opening for a short time.
I mean, no. Why decrease? See, before I put the turbulence, why this without turbulence also this is decreasing here, right? This is completely closed system. Why is this decreasing at all?
But it can oscillate. But here
Even oscillation. Entanglement, completely closed system. Why is the entanglement changing at all? It should be a flat line.
it can oscillate in a closed
Maybe
system.
continue.
Okay.
Fine.
What is the, so I understand entanglement when it's between two spins, but what is the physical understanding of entanglement between theta and
It is same. So your spin I can translate into polarization. So if you want to show the entanglement of polarization or of spin, you cannot just show it by having correlation in horizontal vertical basis. Just one set of basis is not enough. So you will show that in the correlation horizontal vertical basis. At the same time, you will show it that in the 45 minus 45 basis, or you can be left circular, right circular, sigma x, sigma y, sigma z.
But the
and so on.
point is, so when we talk in terms of the spins, we have like consider bell state, that's like up, up, plus, down, down.
Yes.
So we are considering a particular position of the spin,
Mhm.
but here theta is a continuous variable,
Yes.
and if I want
No, I get your question. So whether it is discrete as polarization or spin, or continuous as position moment or angular momentum, the basic physics remains the same. And that is that you have to show, for entanglement, you have to show simultaneous correlation in two different conjugate bases. For the case of polarization, the two conjugate bases can be HV and 45 minus 45. For this continuous variable, the two conjugate bases can be position momentum.
I mean, I get that the theta and L.
And could be theta and yes.
What values of theta and L? At
Doesn't
what
matter.
values of theta? And
So
L
this
would it be?
absolute value of theta doesn't matter. Of course, it will matter maybe in an experiment, maybe it works on a range of theta, but this absolute value of theta doesn't matter. So theta is some value. So you detect the first photon at theta equal to 0, and then depending on that conditional measurement, then you ask what is the range of theta over which I can find the other photon. You could have looked at this theta at theta equal to pi by 2, or theta equal to pi, or any angle, And then you can still ask the question, okay, what is the conditional uncertainty in the theta of the other photon? And that becomes your delta theta. And so this delta theta almost doesn't depend on the theta I, the first theta.
So I'm sure you have more questions. So what I find amazing is the simple layer, hair dryer can bring the entanglement back. So that's really, I think that's your
Yeah, that is
this,
very
right, very hard to understand.
So that's the punch for social media posts.
Yeah, it's hard to, it's amazing. Yeah, good. Okay, so let's thank Professor Anand. It's very interesting.
Thank you so much.
Take a photo.
Oh, photo, yeah. I think all can join. Huh?
Then a group photo.
Oh, okay.
First, the gift photo.
Ah.
Thank you so much. Yeah.